We now want to learn how to take the calculus that we've learned and use it for some very useful applications. And the applications that we're heading towards are called optimization problems. With an optimization problem, you're trying to find the best way to do something. For example, when you're building something in a factory, you want to find a way to minimize the amount of material you can use. That will help you minimize the amount of money you spend to produce your product. On a rocket, you want to perhaps you want to maximize velocity so that you can escape the bounds of gravity. On a windpipe, you might want to be able to maximize the amount of air that you can pass through that pipe. If you're perhaps working in a mine and you're trying to get fresh air down to the miners, you might want to maximize and minimize lots of things in business applications as well, medical applications. So if we're going to maximize and minimize things to do things in the best way possible, there are going to be a few definitions we need. And these definitions are going to establish a couple of different types of maxes and mins. Let's say we had a function that starts right here. That point right there is the first point in its domain, and it behaves thusly. All right, this is what our function looks like. We'll call this point the x value corresponding to that A, put a B here, C there, a D here, an E there, and we call that point F. F might not be the best name for the name of an x value, but okay. All right, so what we have here are examples of both absolute and local extremum. First of all, the absolute. The absolute max is going to be the absolute largest value that the function takes on over its entire domain. It is sometimes called a global max. And for this particular function, we have an absolute max occurring at F, at the x value that I've called F. That function reaches the highest point that it reaches over its entire domain. We have an absolute minimum occurring at the value E. This is the lowest point the graph ever passes throughout its entire domain. All right, so we're going to have absolute maxes. Again, those being the absolute largest value that it reaches. Think of it graphically as the highest point the graph ever attains. We're going to have absolute minimums being the lowest point the graph ever passes through over its entire domain. Those are, I think, pretty clear cut, pretty straightforward, pretty obvious. But there are also things called local maxes. Sometimes local maxes are called relative maxes. Local mins can't be called relative mins. And a local extremum, a local max or a local min, is a point such that if you put that point in an open interval, it will be either the largest or the smallest value in that open interval. So if we start over here with the E, for example, if I put that in that open interval right there, then this point is the lowest point in the open interval. That tells you that at E we have not just an absolute min, we also have a local minimum at E. We have right here a local max at D. We have a local min at C, because I can put that in an open interval. But what about A? What about F? F was your absolute max, but F is not a local max. It is not a local max because I can't put an open interval around it and stay within the domain of the function. This side of the open interval ran beyond the function's domain, and the same thing is going to happen here. A, even though it is lower than some things around it, I cannot put it in an open interval and stay within the domain of the function. Therefore, A is not a local max for min, not a relative max for min, not an absolute max, not an absolute min. A is none of the above. All right? So what that means is that even though absolute extremum can occur at endpoints, absolute extrema can, local can't. All right? Local have to be basically somewhere within the domain where you can put an open interval around it. Notice that an absolute max may be a local, but it doesn't have to be. A local could be an absolute, but doesn't have to be. All right? So an extremum can be one, it can be the other, it can be both, but it doesn't have to be both. It can be one or the other without being both. All right, so be aware of that. Also note, what's noteworthy is that if we look at a function like a sine function, like a sine wave, notice that right here we had an absolute max. Right here we had an absolute min. Over here we had an absolute min. This absolute max is a local max. This absolute min is a local min. And so is that one. So these maxes and mins do not have to be unique. They might be unique, but they can definitely be repeated. So there is a theorem or two that we're going to learn, and these are ones that you're going to want to know by name. In the past, I really don't advocate in a pre-cal class or somewhere like that. I don't advocate for students memorizing the names of particular theorems, but we're to a point to where we should. All right? And there's a theorem called the extreme value theorem. And the extreme value theorem says that if a function f is continuous at the closed interval from a to b. So if you have a function that is continuous on the closed, then there exists there's going to exist a value c that's an element of this closed interval such that f of c is an absolute max. All right? So this is basically an existence theorem. This theorem does not tell you how to find it. We're going to get to that. But this theorem alone simply says that such a thing exists. So it is guaranteeing us that for continuous functions on closed intervals, that somewhere in that closed interval, there's going to be an absolute max. The theorem goes on to say, and I don't think I really need to write all this out, it says the same thing for an absolute min. It says that if you have a continuous function on the closed, then there exists a number in the closed that is the absolute minimum. Okay, again, this is an existence theorem. It simply tells you that it's there. It simply tells you that it exists. The theorem, the proof of it is complicated enough that most books omit it from a calculus text at this level. So we move on with Fermat's theorem. And this is not Fermat's last theorem. If you've heard mentioned at some place or sometime that famous theorem, this is not it. This is just one of Fermat's theorems. And Fermat's theorem says that if f has a local max or min at some number c, and f prime of c exists, then f prime of c is equal to 0. All right, this is basically saying that if it has a local min or max at a value c, and the derivative exists at c, that derivative has to equal 0. Notice that this theorem is a one-way implication. It is an if-then statement. It only works in one direction. All right, this is a single direction in which this thing works. All right, so it's saying that the presence of a local max or min and the existence of the derivative implies in one direction only that derivative has to equal 0. Right? And it kind of makes sense if you draw a few pictures. If you go back to something that has a few hills and a few curves to it, if you look right here, that would be a local max. And if you were to imagine the tangent line at that point, it would be horizontal. Right here's a local min. And if you imagine the tangent line at that point, it would be horizontal, slope of 0. Imagine a tangent line there, slope of 0. Imagine a tangent line there, slope of 0. So what this tells us, again, it does not say that a slope of 0 automatically means max or min. What it's actually saying is that anywhere you have a slope of 0, that is an excellent place to look for a max or min. It's not a guarantee you will find one, but it would be a great place to check for one. As a matter of fact, we have these things called critical numbers. And I will warn you that different books give slightly different definitions to what exactly a critical number is. But the definition that I learned, the one that this book goes with, and the one that we're going to go with, is that if f prime of c is equal to 0, or f prime of c does not exist, that makes it a critical number. Okay, that makes it a critical number. All right, and again, what that's going to account for, another sketch here, is anywhere you have a curve, the f prime equals 0 would locate for you this point. F prime of 0 would locate for you that point. But what about this do not exist? Well, the do not exist will locate for you points like this. That point right there, its derivative doesn't exist because the slope on the left and the slope on the right are not the same. So that derivative at that point would be one of the do not exists. And as you can see, it's another great place to check for local maxes or mins. So what that brings us to is what's commonly called the closed interval method. All right. Closed interval method says if you want to find an absolute max or an absolute min or both on a continuous function on a closed interval, here's the steps you need to take. Number 1, find the values of f at all critical numbers. All right, you want to evaluate f at all critical numbers. And of course, as you find these critical numbers, they're going to generally be numbers that are in the interior of the function, meaning numbers that only show up on an open interval, right? Since endpoints of the interval typically don't show up as critical numbers, or in this definition don't, you're going to find the values of f at any and all endpoints. All right, and from all of these values, the largest is the absolute max. Smallest is, let's say is here, absolute min. All right, so you're going to compare critical values to endpoints, and from there, you find your absolute maxes and absolute mins. All right, closed interval method. Let's use it. Let's put it to use a couple of times. What if I had an f of x equaling 3x squared minus 12x plus 5? That's a quadratic. And on the interval from 0 to 3 is where we're going to look. So I'm going to take the derivative, and that's going to be a 6x minus a 12. I take the derivative, set it equal to 0, and I get x equals 2. All right, so to make life a little bit easier, we'll do this part on the calculator. I'm going to put the 3x squared minus 12x plus 5 into my calculator, pull up a table, and let it give me some x and y values. I'm going to put in a 2 first, and the 2 gives me a negative 7. Put in the 0 next, it gives me a 5. 3 next gives me a negative 4. Okay, of these numbers, 5 is the largest. So this tells us the absolute max is at 0, and the absolute max is equal to 5. The smallest of these numbers corresponds to the x value of 2. So the absolute min is located at 2, and the absolute minimum value is a negative 7. All right. Now, ironically enough, we are able to find with this method, we're able to find absolute maxes and mins. As of now, technically speaking, we're not able to find local maxes or mins, but that's coming soon. All right, we can take this method, we can add more to it, add a little bit more substance to it, and we will be able to locate locals, but for now, it's absolutes. All right, so let's try that one more time. Let's say I had an f of x equaling a x squared minus 1, and that thing's cubed. And we're going to do it on the interval from negative 1 to 2. And again, my theorem guarantees that they're going to be there, that these absolutes are going to be here, because that thing is continuous on that closed interval. Okay? So, f prime of x is going to be a 3, the power comes down, x squared minus 1 to the second power, times, we'll come inside for a chain rule, and we have a 2x. 3 times 2x is a 6x. Make that look more like an x and less like a lambda. And there's my derivative. All right, there's my derivative. Setting the derivative equal to 0, lucky for me, it's already pretty well factored. When I set 6x equals 0, I get x equals 0. When I set x squared minus 1 squared equals 0, I get x equal 1 and negative 1. All right? So those are my three critical values. And can a critical value turn out to have been one of your endpoints? Certainly, it just did. All right, so I will put the original function, clear out the old, put in the new, put in the x squared minus 1 to the third power in the calculator. Go to my table and put in a 0. 0 gives me negative 1. Put in a 1. 1 gives me 0. Put in negative 1. Negative 1 gives me 0. Put in the 2. 2 gives me 27. Okay, so the absolute max is located at an x value of 2, and the absolute max is equal to 27. The absolute minimum is located at an x value of 0, and the absolute minimum is equal to a negative 1. Right? Closed interval method. Very straightforward, to be honest with you. Very straightforward approach as well.